today we will be covering minimum moves to reach target with rotations problem from lead code. And in this problem, as you know, we are given a snake and a grid. So let's start with the given sample input. This is 6 by 6. And we have the snake on the left now. Like I represented it with snake back, and I think that's it. And our desired end location is, let's say, final snake back and final snake front. So basically, we want to start from here, and then we want to reach here with the minimum number of moves. And like obviously this is a graph traversal problem. Like this grid, we can represent this as a graph, right? And it requires minimum number of moves to reach from one point to another. So when we see a minimum number of moves in a graph traversal problem, it's better to think for BFS rather than DFS. The reason is, like with DFS, you can still find the minimum, but you're going to try many different ways. Because without trying all the ways, you cannot guarantee that a path is minimum with DFS, right? But with the help of BFS, since you visit things by their distance from the starting point, whenever you reach their point, it is guaranteed that that point is reached through the minimum length or shortest path. Any questions up to this point so far? Like we solve the problem, we see that it's a grid and it's starting from one point and going to another point with the minimum distance. Therefore, what we are going to do is we are going to think of this as a graph, and we are going to use BFS to get from the start point to the end point. I think up to this point, it was very easy to detect, right? So in the context, people who had time to spend on this problem, were you able to see it clearly? Can I see hands? Like how many people had struggled with seeing that they are going to use BFS and they are going to convert this to a graph? Can I see hands? How many people struggled with it? So you struggled with it. What was the reason?
I thought BFS would work as fast.
Okay, but now I think this explanation is clear now, right? Like these keywords, we should make use of them, and we should understand the way our algorithms work. And probably in your implementation, you were checking all possible paths, right? So because the first path you find, it's not guaranteed that it was shortest. But in BFS case, it's going to be guaranteed. So that's why it's a better fit for this problem actually. Because it's going to give us a better time complexity, right? Like you find one path in n plus m time in DFS, but you have to be looking for all the paths, so you're going to be visiting the same edge again and again. So your time complexity is going to be higher. But in the case of BFS, it's going to be n plus m, where n is the number of nodes and m is the number of edges. Yes?
What about in cases when we're required to find the longest path?
What's that?
What if when we're required to find the longest path?
Then you gotta go with the DFS to check all the... Yes. Unfortunately, like you guys can search for it. Like it's actually a very fun problem. Unfortunately, we don't have a very good algorithm to find the longest path. Like it's very interesting, right? Like we can find shortest path very easily, but for longest path, the algorithms that like it's an empty complete problem. That's that's quite interesting, but that's what it is. So, after making these observations, let's think about what can be challenging in this problem. Like first off, normally, we are moving with one cell, right? Like our character usually occupies one cell in the grid, whether it's a mouse or cat or person, I don't know. Usually they occupy one spot, one cell. However, in this problem, our character is occupying two cells, right? That's the first thing that we should be careful with. So when we are checking whether we visit somewhere, instead of looking at one cell, we are going to be looking at two cells. First off. Another observation is, obviously since our size is different, our moves are going to be different. Like once we have one cell, relative neighbor coordinate difference is very easy to define, right? if we are using the main ones, like main directions, it's going to be these 4 guys. And if we are using also the like these guys as well, it's going to be 8 in total, right? But in our case, it's going to be different. So, for this, in order to understand what kind of possible moves are there, we need to refer to the text. Like there are 4 types of moves possible. The first one is move one cell to the right if there are no blocked cells there. So, let's go back to here. Now we don't have 1. Like we basically have 2 cells, right? And move one cell to the right is this kind of a move. So now let's define our relative neighbor contract, relative neighbor coordinate difference array. So how many different neighbors we are going to have? Let's start with 4. If we need more, because there are 4 possible moves, that's why I start with 4. But if we need more, we can define more. And how many relative coordinate differences are we going to have? Normally it was 2, right? X and Y coordinates for the cell that we are occupying. But this time, since our snake is actually occupying 2 cells, we are going to need 4 different updates. 2 for one cell of it, and 2 for the other cell. So that's why it's going to be a 4 by 4 array. And the first one that we detected so far, once we move 1 right, let's say we start with these 2. Like first we were occupying this one and this one. Now we are going to be occupying this one, like this is first, this is second. Now we are going to be occupying this one and this one. So can you tell me the relative coordinate differences for those? I'm going to need 4 numbers here.
0, 1, 0, 1.
0, 1, 0, 1. What is the reason for this? Like basically, if you look at that, is my column number changed? Yes. Is my row number changed? No. Therefore, no updates for the row numbers and 1 increase for the column numbers. This was one move. Now let's take a look at the second move. Move down 1 cell if there are no blocked cells there. This move keeps the horizontal vertical position of the snake as it is. So, let's say this is our snake again. This is my first one. This is my second one. After the move, like let's say this is first one, second one, this is going to be first 2, second 2. And here, it's going to be first 2 and second 2. Right? And as you see, like we are actually considering one case of the snake. Does it really matter in terms of relative coordinates whether the snake is looking upwards or sidewise? It doesn't matter. Like what we are focusing on the relative coordinate difference. So, for the second neighbor, what are going to be the coordinate updates?
1, 0, 1, 0.
1, 0, 1, 0 this time, right? And we have one more move, 2 more moves. Let's look at the first one. Rotate clockwise if it's in a horizontal position and the 2 cells under it are both empty. In that case, the snake moves from RC and RC plus 1 to RC and R plus 1 C. It actually told us. Like we don't even have to think about the relative coordinate difference, right? RC to RC means 0, 0. And how about the other one? It says RC plus 1 to R plus 1 C. Meaning plus 1 minus 1. Is everybody clear with this? Yes.
I mean, what are the specific representations for each component in the 4-member list? I mean,
So first 2 represents relative coordinate difference for head. Like let's say this is snake beginning. Or like this one, you can think of. Relative coordinate difference for tail. You can think of.
In that case, the third one, we're moving the head around, not the tail. So shouldn't we flip that?
Okay, so basically you're saying this is tail, this is head?
Yeah.
Okay. Thank you very much. I wasn't paying attention. And it's important. Like maybe because of this part I would be looking for what is going on in the code. Thank you. And let's look at the fourth one. Again, for this one, the coordinate difference, relative coordinate differences are given to us. So the first one is like it goes from RC to RC, and the second one is going from R plus 1C to RC plus 1. Meaning the second one is plus 1 and the first one is minus 1. Indeed, what we can do is, like it's better to first have the head and then the tail, right? Because that's how we are going to apply the update probably. Let me think. No, I think it's better. Like we are going to represent it like this. Let's keep it like that and then we can decide on it later. So, any questions about how we define the neighbors array? Is this clear? Like first, what we should decide on is how many different neighbors do we have? How many different possible moves do we have from a given state? And since there are 4 different moves, that's why this dimension is 4. Second, with how many coordinates or like with how many cells, with how many different whatever, we represent one state. So here, we represent one state with 2 cells, and for 2 cells, how many coordinates do I need? 4. That's why this is 4 by 4. And the reason I'm suggesting implementing it this way is, even if we had this bug, let's say after the implementation we get wrong result, then we know where to look for. Instead of going over like 4 times copy pasted BFS implementation, we are just going to go take a look at here. Okay? This is a very compact way of representing the same information for the neighbors. Okay, now that we know our neighbors. Yes?
Where is the origin?
What's that?
The origin, the starting point.
Yes, this is the beginning.
And
I think, does the question specify it or is it always starting from left up and going to the right bottom?
Yes.
I think that is the case, right? It always starts from the left up and going to the right bottom. Yes. So, now that we know about our neighbors, the second thing that we should consider, we should be very careful with is, how are we gonna decide whether a state is visited or not? Like, I basically underline the word state. I'm not saying cell. Because in some questions, as in this case, states can occupy more than one cell. Or maybe the way you enter the cell can be part of the state. That's why we are focusing on the state rather than the cell. Okay? So now, let's think about it. How can we represent one state?
Holding 2 cells at the same time.
What's that?
Holding the location of 2 cells.
Yes, like basically where is my head and where is my tail? Depending on this, I can distinguish all the cases from each other. So, meaning, what am I going to have in my visited array? Like as indices.
Array of coordinates.
Array of coordinates. Like basically I need 4 numbers.
Yeah.
That's how I represent the states as well. Now that I know how to represent the states as well, is there anything that I should be careful with before starting implementation of BFS? Like once you are clear with your start position, end position, your neighbor relations, as well as how you're going to represent the states, I think it's time to start implementation.
Emre,
Yes.
I have a question.
Yes.
I mean, my problem is with the coordinate representation. So if we say the coordinates for tail, 0, 1, right?
Coordinates for tail. So this is not the coordinates for tail, but this is relative update to go from xy to its neighbor.
Okay, after it moves to the neighbor? Okay.
Yes, so basically like the problem tells us there are 4 possible moves. So with the help of this array, given x1, y1, x2, y2 for the snake, with the help of this array, I can find one neighbor for each of the elements in this big array. Meaning like all these like 1, 2, 3, 4 arrays, they take me from one cell or one state to a neighbor state. Okay?
So just adding the members will take me into a neighbor.
Yes. So basically, in the implementation, we are going to say nx is equal to nx1 is equal to x1 plus neighbors 0, 0, and then we are going to say ny1 is equal to x2 plus neighbors 0, 1, and so on. Did you get it?
Yeah.
Cool. Yes.
Why is it containing 4 lists? Is this the
This one or this one? Which 4 are you talking about?
the second?
The second one. Okay, let me explain both. The first one is because we have 4 neighbors. For any given state, there are up to 4 neighbor states that we can pass through. That's why the length of the first dimension is 4. And the length of the second dimension depends on how many different elements do we need to represent a state. Like in a usual problem, if it was only one, the snake was occupying only one cell, how many coordinates did I need to represent one state? It was 2. If it was occupying only one.
It was occupying 1.
If it was occupying
Yeah.
only one, I would need only x and y, right?
Oh, okay.
But now that since the snake is occupying 2 cells, that's why I need x1, y1, x2, y2. Is this clear? Like this is very important. Is this clear? Okay. Thank you. Any other questions? Like if there is something that is not 100% clear, please ask it. There is no wrong questions. Yes.
Okay, so the first move would be 0, 1, 0, 1. So where would it take the snake, this coordinate?
To the right. Yes. So now let's take a look. Like an x1, we said x1 plus neighbors 0, 0. Neighbors 0, 0 is 0. Right? So x didn't change. And ny1 is equal to, sorry, this is y1. I'm sorry. y1 plus neighbors 0, 1. So basically, the x coordinate did not change and the y coordinate is increased by 1. So it moved to the next column.
That's actually
And the same update is applying to the other part of the snake as well. So it's taking the snake one right.
I think you've mixed up, you've interchanged x and y. I thought y was supposed to be represented this way. How did you represent x and y?
Like if we say x to this and y to this,
Yeah.
this is going to represent x, this is going to represent y. I think.
Okay. That's fine.
Like usually in computer world, we use it in the reverse way than math. So like choose one, but like most of the implementations are this way because of the way arrays are defined basically.
Okay, so for the second move, 1, 0, 1, 0, I mean, it is allowed to move to the left?
No, it's going to take us down. Like if 0, 1, 0, 1 is taking us to the right,
Yeah, x is
0, minus 1, 0, minus 1 is going to take us to the left. Okay? Is it clear now?
Yeah.
Perfect. Any other questions? All right. So then, let's start the implementation. All right. So I'm going to use C++. And like basically in order to represent the states, like we can basically define our own class or a struct which is going to have x1, y1, x2 and y2. And let's say return 0 just to make sure we are able to work with the state, like I want to define a state, x, and then want to say like x dot x1 is equal to 1, x dot x2 is equal to, x dot y1 is equal to,
Computation has started, right?
what's that?
Computation has started.
Yes. Like right now, we expect it to give wrong answer, but we expect it to write something to the screen, so I forget to put the space in between, and as you see, it printed out 1, 2, meaning I am able to define states. Like again, like our approach is, once we write a small unit, then we are testing it, so that if there's a problem there, we are gonna solve it when it is just when it is still in our cache, very fresh in our memory. Okay, we verify that we are able to define states. Now we will continue with our implementation. So we are given the grid, and grid actually represents the map that we are going to use. That's fine, and we know that the initial start point of the snake is, yes, sure. How about now? Okay. So the first thing that we should decide is the start coordinates of the snake, right? And in the board, we were representing it with snake beginning and like snake back and snake front, I think. Okay, let's stick with that and say it's actually not going to be SP, or actually we can take a state, right? Because we are going to be dealing with the states. State start, I'm going to say, and then I'll say start. X1 is equal to 0. Start that Y1 is equal to 0. So 0, 0 is the first one, like the back. And then I have 0, 1, right? And what do I need? Like, since I'm going to do BFS, basically I need a queue, right? And my queue is going to contain states. So now, just to see that everything is working as expected, again I'm going to run it. And we have a problem.
I think we haven't defined.
It's not insert, maybe it's a different method. Like
NQ?
it's NQ? Okay.
No, I don't know. It's NQ and shit.
Okay. C++. I mean, once you deal with many languages, like sometimes all these keywords, they can get mixed with each other. I think there's push. Inserts elements at the end. It's a queue. Yes, that's exactly what we need. So we are going to say queue.push. So now let's give it a try. Okay, so it runs as expected. We don't care about the result yet because it's a half-baked code. And after that, as long as the queue is not empty, so there is empty function for that. First, what are we going to do? We are going to pop, right? Is it called pop? Removes the first element. Yes. I think in C++ we have to get it with top. Q.top. And then we need to remove it. Like, this is annoying. Pop is void. Okay, so now that we get the current element, we actually have a need for our neighbors array, right? So let's define it. Can somebody just read me?
Okay. 0101 1010 0, 0, 1 minus 1. 0, 0, minus 1.
Minus 1?
1.
1. Okay. So, now we get the current state of the snake, and what we want to do is we want to check out its neighbors, whether they are visited or not. Oh, actually I also need to visit it, right? And for visited, what I can use is, I can just use a set, right? I can insert these states into set, and then check whether that set contains a given state or not. And after this, I will also, after popping, I'm gonna here mark this guy current as visited. Or when we are pushing it, I think it's better to mark them as visited when we are pushing. So I'm gonna do it here. So visited, it's a set. I think it's insert, but let's just make sure. Find, erase, insert, yes. Visited.insert, start. So now that we get the element, what are we going to do next? We are going to iterate over our neighbors and see whether they are visited already or not. I have 4 neighbors for sure, so this for loop is going to iterate over 4. And inside, what I'm going to do is I need to define the new state to consider whether it's a valid state or not and check whether it is visited or not. So I'm going to say state neighbor, and then neighbor that x1 is equal to current dot x1 plus neighbors I0. So, except these like exceptional cases, I don't suggest doing any copy paste, because even if I'm copying and pasting like 3-4 lines of code, usually I do bugs in there. Like in my experience, this is dangerous. But like for such trivial cases, you can do that. But in general, I don't suggest copying and pasting. Just write it again. It's not going to take too much time. But this is very straightforward, and we can do the check very easily, right? So we are updating x1, y1, x2, and y2. y2. And then we are going over 0, 1, 2, 3. Okay. Any questions up to this point? Now that we actually have a candidate neighbor, we should check whether this is a valid state in the map or not by checking both elements are in the boundaries or not. So and I have the grid, like basically I think the sizes are, it's better to get them initialized here. Like let's say n is equal to grid.size and m is equal to grid's 0.size.
I think it's the same, right?
What's that?
Isn't it supposed to be the same?
For the question, maybe. It's right. I guess, yeah. But like in case they are different, it's going to be the same thing. Are they the same in the question? Okay, then we only need n.
But if it wasn't, we would have to not 0, right? I for each.
Say it again. I didn't get the question.
If there was m,
Yes.
would we check array of 0 and n?
Like in that case, like if the sizes were different, then I would do it this way. The reason is like in C++, like since this is a vector of vector, right? Grid is a vector of vector. And the size of one dimension comes from the size of the vector itself. And the other dimension comes from the size of each vector inside of this vector of vector. Are you able to see that?
So it always checks the first list?
I mean, first one, second one, third one, you can use like 1, 2, 3, but like maybe 3 doesn't exist. They all have the same length. Because it's a rectangle, right, in that case. But right now we don't need this because it's always square, so I'm going to leave it like this. Int x1, y1, n, and the other coordinate that I should check is, oh, actually it's not x1, it's neighbor dot x1, neighbor dot y1, n. And the second one is neighbor dot x2, neighbor dot y2, n.
Are we checking if these are inside the borders?
These are inside the grid or not. This is what we are going
Why,
to check.
why don't we do all in the same function?
What do you mean by?
I mean, neighbor x2 and neighbor y2. Why is it different?
Like, because basically here I am checking whether SL is included in the grid or not. And if you don't use a helper function here, you're going to have this like four statements. X is greater than or equal to 0, smaller than n. Y is greater than equal to 0, smaller than n. So it's going to be a dirty code. That's why. You can do that. After finishing this, let me also show that version, and then we will see why I prefer this.
Yeah, but can't we just collect them all and then compare them if they're inside n?
What do you mean by?
Like
I mean,
neighbor
inside
x1,
function
neighbor
has
y1.
5 parameters. x1, y1, x2,
Yeah,
y2,
and
and
at the end there's n.
I mean, you can do that too, but in that case, it's going to be the same if. That's why. Like, let's see 3 versions in the end, and then I will explain why I find this more readable.
Okay.
I mean, it's also doable without the function, right?
Mm.
I think this is more readable. Okay, so we check now whether both cells are inside the grid or not. And after that, if they are both inside the grid, what else should I check? Whether this state is already visited or not. So this is a lame way of checking it, but this is C++, that's why I got to do it this way. So basically, if the find function cannot find the element, yes.
So we check if the cell is blocked or not.
We are going to check that too. That's a very good point. Thank you. Thanks for reminding. And we will have one more end condition. Let's check that one first. Grid. Oh, actually, inside, we can basically check like inside, and we can make this function inside and free. Inside free.
By the way, inside free, I mean, this method is your personal method, right? It's not default.
Yeah.
What's that?
Yeah.
It's your own, it's defined by you, right?
Oh yeah, we are gonna, yeah, exactly.
I was
It's not, the languages are not that smart yet.
Yeah.
And when they are that smart, I don't think they are gonna need software engineers anymore, so you should be looking for a new job. Okay, we also need to pass the grid right now.
Then we don't have to test them.
Yes, good point. We don't need the n anymore, so we can get rid of this guy.
We can. On this one, the blocking conditions change for the rotations and the sideways. For the rotation, there's an additional check we have to make.
Like the okay. That's a very good point.
We should also pass I maybe.
Pass like which move it is?
Yeah.
Okay. Thank you very much. Yeah, that's a very good point. Is everyone clear with that point? Like basically for the rotation moves, if the like it's diagonal cell is blocked, then the rotation is not allowed, right?
The bottom 2 for the clockwise and the right 2 for the counterclockwise.
Okay. We are going to refer to the definition when we are writing inside free function. So now let's continue doing it top down. And after that, like basically if we are inside of this if, it means we are actually dealing with a neighbor that is not visited before yet. So what we should do is, as we apply to the start, we should push this guy to the queue. Oh, by the way, we used visited as set, but at the same time, do you guys see that we actually need the distance, right?
Yeah.
So, but is it better to keep it in the state? I think it is better to keep it in the state because we are going to need it in the state. So let's add distance. So at the beginning starts distance is 0. Right? That should be fine.
I mean, if, we should increase the distance by 1 if it's not visited, right?
Not all the time. Like if you don't keep it here,
Okay, yeah. If it's already
if it has more than one neighbors, then so it's better to keep it in the state. Okay, q dot push neighbor, and one last thing we should do is visited dot insert neighbor. Okay, and in the end, like we should check like once we are dealing with the endpoint. So here we can say if neighbor dot x1 is equal to, let's also define end here. What is my desired endpoints?
N minus 1,
N minus 1, N minus 2. N minus 1, N minus 2.
What was it again for x1?
N minus 1. N minus 2. No, I think. Okay.
N minus 1, N minus 2.
N minus
I think
N minus
it's, no, it's all the N minus 1 for the second.
What's that?
N minus
This is n minus 1, yes. Okay, so now I'm going to check if it is equal to my endpoint. If I find the endpoint, then I'm going to return the distance of the neighbor, right? And if that is not the case, if I
There is
reach
a
here,
typo in neighbor.
excuse me. Eyvallah. Thank you. And here we are going to return -1 if we couldn't reach to the endpoint, right? Okay, so what is missing? There is only one missing thing. We need to define inside free function, right?
Have we checked the whether it's vertical or horizontal for the clockwise turns?
What's that?
Have we checked the fact that it's vertical or horizontal
For what?
for clockwise and anti-clockwise turns?
It's going to be done in the inside free function.
So it's horizontal. I couldn't see it.
Oh, we didn't implement inside free yet.
Okay.
So we are approaching top down. Like basically you can use this, but the risk is like if you leave one function empty, then you're not going to be able to check the logic of the other part. But since like this is a straight VFS implementation, I didn't see any harm in that, and then left that part before implementing inside free and coming back here and finish the BFS implementation first. Now I am diving into the inside free box.
Yeah, but that's I thought that was supposed to work on the new node, right? On the neighbor node.
I don't think I get the question.
We're talking about the neighbor node, right? The inside free works on the neighbor node.
Yes.
So we're gonna check it on there.
Check it what?
Check the fact that it's horizontal or vertical. I'm talking about the original state. Like for example, if the original state is not horizontal, you can't turn anti-clockwise. Like if it's horizontal, you can't turn anti-clockwise.
We can return false in inside free, I think.
Yeah, we can do that. But
So basically,
We
how
have
are we
to
going to
test-
be able
test
to?
all the values of neighbor to inside free to check that because
Yeah, but
we are trying to understand if it's horizontal or vertical. Inside
But we
free.
don't know the original coordinates. I think that's what you're
I think
saying.
We can pretty much assume, though. I mean, if the new node is vertical, then we can assume that the original is horizontal. So,
Yes.
Yes,
We
can
should
do
be able to, yes. Like basically by looking at the new coordinates, we should be able to figure that out. Okay. But I mean, it's going to be done inside free, and if we need more parameters, we can easily pass them. Okay, but thanks for reminding. Okay, so now let's go ahead and implement inside free function. And let's get this guy because like this is a trick that I am using when I'm diving into a function with multiple parameters because you need to remember the order of the parameters, right? What is this guy is going to return? It's going to return a boolean. And x1 is an int and x1 and y1 is ny, or it's not 1, like it can be nx. Oh, actually this is not possible, right? Because we are passing only one parameter. We are not passing the neighbor.
Can we just pass?
We can
the
just pass
state?
the neighbor. Yes. Just gonna copy the signature of this guy from here. Not signature, but the type. The full parameter, let's say. Neighbor no, let's say. Alright, so the first thing we should check whether the cells are in the grid or not.
I think we can create a function for this too. Because we're gonna write it 4 times.
That's fine. Because it's short enough. I mean, it's just like a very small implementation detail. You can do that. Or we can basically define n instead of calling the size function 4 times. Or we can just pass that. N is already here. I think we completed our loop, right?
Yeah.
With So if one of these conditions are satisfied, then we are going to return false. It means like the cells are out of boundary, right?
I think the last or is unnecessary.
Not just unnecessary. We got deleted. Okay, so now that, like here, if we hit here, it means like both cells are within the grid, right? So now check the other conditions. Let's check the other conditions. I might actually need, we are checking the visited there, and I have the grid, so we should check whether the cells are occupied or not. Actually, we can continue here. Or,
Oh, it was not unnecessary.
grid neighbor x1 neighbor y1 or so since the execution starts from the first part of the condition, this is going to be okay. Are you guys clear with that? Because if we start from the end, if the neighbor was not within the grid, then we would get exception, right? Or in C++, we would get runtime error. Are you guys clear with that? But since the execution order is like it first starts from the first condition and then second and so on, if the neighbor is out of boundaries, we are going to detect it first. That's why it's going to be okay to write the code like this. And at this point, we know that we have a, yes.
I didn't get the last two conditions.
Okay, so if, like, because it's a grid, right? Some of the cells are occupied. And we are not allowed to move the snake over the occupied cells. So that's what we are checking with the last two ones. Like this basically says like if this is equal to 1. Or if it basically says like, says whether it is not equal to 0 or not. That's why. Okay, so if we reach to this point, it means our cell is valid and it is not visited. So what we should check is whether it is a valid horizontal or vertical move thing or not. Oh, actually that's not the case. Depending on neighbor no, we might have to check some other cells as well, right? If neighbor no is equal to 2, which move was this? 0, 0, 1, minus 1. So what are we supposed to check here? First, let's check like
Never know means which here.
like we are talking about this one, right? Meaning our column, our row is increasing by 1 for the
I think
for the head.
it's the diagonal move, right? For this one.
But which diagonal move?
I mean,
Clockwise.
clockwise, right?
And this one is counterclockwise. Or usually we represent them with CV and CC. So if it is a clockwise move, because with 2 we are at clockwise move.
We only need to check extra. Let me see. Y2 is the head or is it the tail?
Y2 is the head.
Y2 is the head.
Then we should check Y2 plus 1.
Yeah.
Neighbor dot x2 and yes.
X2 is
What
already
does
checked.
never know means? I mean,
No, no.
On the grid.
We need 2 coordinates basically for a cell.
Yeah. Emre,
Yes.
what does never know means? I mean,
So neighbor no means like which neighbor are we dealing with?
okay.
If it is 2, yes. Y2 plus 1, right?
Yes.
This is the one that we are supposed to check. Then we are going to return false. Is there any other cases that we need to check? Like basically we should also check whether this, like the snake is vertical or not, right? So for that basically we should check like this clockwise move is only allowed if our snake is
Horizontal.
horizontal. So if our snake is horizontal, what does that mean? If it's horizontal,
Right now it should be vertical. Neighbors should be vertical.
no, if our snake is horizontal, at the beginning, then it should be vertical right now. If my snake is vertical right now, what does that mean? My column numbers must be equal, right? We can say, or my column numbers must be equal, meaning my column numbers are wise. I think that's the case, right?
Is it or is it and?
Or, if it is occupied, or, because we are returning false.
Emre, we're checking whether the move is valid or not, right?
Yes. So for the move to be invalid, it's either the diagonal cell is occupied, or we are not ended up in the vertical position. Because clockwise rotation is only allowed when we are horizontal and we are switching to vertical.
So just like this, right? It has
It's
to be-
clockwise, it's like this to this.
Okay.
Okay? And if we can actually copy this, if the neighbor no is 3, because it's going to be similar, then this time we are going to be actually performing a counterclockwise rotation, and this is only allowed like this, right? So from vertical to horizontal. So it means like which cell I'm gonna be checking,
X2 plus 1.
and Y2. And this time actually if they are equal, that's gonna be the problem. Is that true or no? I think that's true, right? Because we are only allowed to switch from vertical to horizontal. And then here, if we reach to here, it means we did all the checks. There is no extra cell to check if it's a normal, like right move or down move. And no need to check the state as well. Like they are valid in both cases. So we are going to return true here. All right. Shall we give it a try? Run code. Neighbor was not in this. Which row number is it? Line 7.
No,
No, some of the neighbors are incorrect.
What's that?
It's a
Some of
typo.
the neighbors are like they have typo.
Okay.
Actually, a lot of neighbors have typo. Typo ones can be just assumed that they are the correct neighborization. Yes, exactly.
Okay. I always have trouble with this word. Like there is a little too much.
It ends with bor, Turkish.
No, I think the reason is like the keys are very close to each other, so my typing speed is always not always the right one.
That doesn't have any codes.
Okay, let's see. This is Z, this is Q. I think it's front. There should be one more. Oh, there is no. Okay. Oh, yes. Yes, if it is not visited. Let's give it a try again.
Line 63.
963. Let's see.
Is it fine neighbor? Returns boolean over it or something?
This is a set, and then I call visited.find. That looks okay to me. Okay, I'll try it again. Try to see what it is again. Okay, so I think it's not able to compare the state function, like basically since this is a struct, it doesn't know how to compare them, I guess. Let's see. Okay, so we basically need like comparator function that is gonna allow us to distinguish different elements of states. we don't need the order, like actually all we need is equality, so that's why we can just do it for all the coordinates. Or here, x1, x1, y1, y1, x2, x2, and y2, y2.
Are we checking for the validity of the information we passed, or?
No, like we are basically, it doesn't know how to compare two state objects. It doesn't know whether they are equal or not. Like in Python, these things are easy, but in C++, you need to tell.
So we have to use the equal sign, right? Not the less than sign.
No, because it's overriding the less than operator.
Okay.
It checks that one. It doesn't check the equal one. So let's see. Okay. I think this works with the current. Let's see. Okay, so this is the right one, I think. This one is less than other dots. X1 more. It's not full. States. Okay. Okay. So it worked as expected. Now let's give it another input. Like, do we have to copy? Let's see. Let's do this case. I guess we have to copy this part, right?
Yeah, just delete.
Okay, it's about extra spaces here. Oh man, it's gonna be painful.
Can you try Jupyter control base?
Let's try like this. Oh, it
That's
works, right?
painful.
But like, did we delete one more?
Oh, I have no idea. You can just control Z.
Are you sure? I think it's
Yeah,
looking
it's-
something extra. Yeah. What the hell? We're not able to see some part of it. Like, it's weird. Okay. This is lead code thingy. Okay. Let's give it a try now. Run code.
Yes.
Okay. So now, I mean, at this point, what we are supposed to do is to test some good test cases, right? We should come up with them and then test them. But now that we are running out of time for the session, I'm going to click on submit. So I don't suggest you guys doing that, okay? We need to test our code. And I'm being a bad influence right now, but I'm also warning you. What's that? Time limit exceeded. That's interesting.
Can we? Let's check the code again. I think visit it.
We might be, yeah, we might be looking. Let's see. Maybe it's not visiting, it's not adding things to the visited, like that override function might not be working well. Let's take a look. Okay, so basically we can check whether our visited function works well or not by when we add a new element to the queue.
Type.
Oh, yeah, makes sense. We need unordered sets. But would it be the case? What? Okay. So since we are using unordered set right now, we don't actually need the less operator, like we need the equals operator. So this time we need to check the equality of things. Therefore, it's going to be a constant state. Other, let's say, return x1 is equal to other dot x1 and x2 is equal to other dot x2 and y1 is equal to other dot y1 and y2 is equal to other dot y2. Yes. So now let's give it a try. As for hash function, oh, okay, so we need this guy as well. It's not just about this. It needs to be hashed.
Yeah.
Yeah. Okay. So this is a little too much work because of choice of C++, but we got to do what we got to do.
You can just sum up the
Sum or multiply, like with sum we can have collision actually. A multiplication, what are the coordinates? They are very little, right? Multiplication plus sum, let's say.
Actually, multiplication will make no difference.
What's that?
In case one of them is 0.
In case one of them is 0, multiplication is dangerous. That's why I also had some issue. I mean, you can use a better hash function, but if this is good enough, we are going to see. Wait, did we finish
It's
implementing
actually
this?
inside the class. Do we change it?
This is inside the struct, or wait, what's going on? My hash function, I should give that to the unordered sets. Okay. Okay. So now let's give it a try to see if this was the case or not. Yes, it's accepted. Okay, so because of C++ choice, it took a while, but I think that was a very good exercise of like using the language in a right way. Like we mentioned about this at the board, right? C++ is using ordered set and ordered map by default. So if we don't care about the order, if we don't want these operations to happen in log n time, but in O1 time, then we should go with the unordered version of that. So like this can bypass, that's why we should be very knowledgeable of our language. I think that was a good lesson. And also like we had to deal with a lot of stuff, as you see, like we had to define the function and stuff. So depending on these kind of requirements, you might change the preferred language. So nobody's forcing you to use C++. Like you can even solve one problem with Python and another problem with C++ in the interviews. This is allowed, and that's very normal, and you have very valid reasons to do that. So any questions up to this point? Like the thing that I want to remind is, if you really think about your solution well, like the implementation is going to be relatively straightforward. Like here, I think the execution of BFS part was very simple and clear. At the same time, since we define the functionality, like what do we expect, the contract of the inside free function well, it was also very straightforward to implement this one. Like the only challenging part was converting set to unordered set because of this like additional functions that we had to bring in to the game. But overall, I think this was this helped at least like how you're going to implement such tricky BFS implementations. Any questions?
I thought the inside tree was gonna be a lot longer, and it is actually not. It's very shorter than I thought. So it's good.
What are we checking when we are checking for the validity of the rotations?
Say it again.
For the validity of the rotation moves, which is the n neighbor node.
Yes.
Shouldn't we check both sets?
We are actually checking the both sides. Like if you look at the first part, here, like in this part, is it visible?
Yeah.
Okay, so the selection is also, I guess it's not very visible, but like I picked 4 lines starting in the if. So these 4 are actually checking whether 2 cells are included in the grid or not. Because we might be going away off the grid, right? If we are on the border. And after that, we are checking whether these cells are occupied or not.
Not the same, for the rotation parts.
And for the rotation part, we are actually applying 2 additional checks. So for the rotation of 2, this is the clockwise rotation. And in the clockwise rotation, we need to have the diagonal cell to be free. And at the same time, it is only allowed when we are switching from vertical to horizontal. Sorry, horizontal to vertical. So that's why we are also checking whether we are in the vertical position or not. And if we are not in the vertical position, we return false.
And we don't check why 2 plus 1 is in the grid or not, because it is actually already coming from the
Previous check.
Actually, it's coming from the previous state. Previous state.
Okay.
Yeah.
But I think like this is actually it's a good call. Like normally we should have checked that. So we should have said here like.
No, we know actually it's.
Okay, I understand why it is working, but like it's better to check. Like it's better to be explicit because I didn't have that. I didn't have that knowledge. Like when I was writing this, actually this was a bug in my understanding. But now I understand what you're saying. Like it's actually given because of the previous step. But it's better. Like it's just one more check, right? Better to be on the safe side.
The reason we're not checking the cell next to the head is it because we have checked it previously?